I'm Andre. I work in GSI here at OICR, and I want to start off by saying that I hate everything that you love and love everything that you hate. No, I've been thinking a lot because we argue about tools pretty much constantly as a profession, and I've been thinking about how we do that arguing and why we get into some of the ruts that we get into. And mostly I'm going to talk about programming languages because I like programming languages, but I think this applies to pretty much all of the tools out there. So let's talk about languages. I went to Wikipedia and looked up a bunch of languages, and these are the sort of buzzword descriptions of those languages from the paradigm section of the Wikipedia. So Java is an object-oriented, class-based, structured, imperative, generic, reflective, concurrent language, whereas C# is structured, imperative, object-oriented, event-driven, task-driven, functional, generic, reflective, and concurrent. C++ is procedural, functional, object-oriented, and generic. Python is object-oriented, imperative, functional, procedural, and reflective, and JavaScript is object-oriented, prototype-based, imperative, functional, and event-driven. And that leads me to this, what the hell does that mean? Those are all object-oriented languages, but they're very different languages. I'd also like to know, why is Java not functional? Because if C# is more functional and those two are almost identical, wait, and C++ is functional, what happened there? Those terms don't really help us figure out what we want to know about a language. They're very contextual, and they're very sort of splitting hairs about the behavior of a language, and I don't think that's so helpful in comparing them. So let's try to come up with a better way of describing languages where we can actually compare them against each other, which is what we really want to do when we're evaluating tools. And for this, I kind of want to separate the language from the standard library. So let's just take the standard library, as important as it is, chuck it in the bin, and we'll deal with it maybe in another talk. Hint, hint. So the system that I propose is that for every feature in a language, we have two sliders. And one slider goes between how magical versus how explicit or verbose a feature is. Do you have to specify exactly what you mean, or does it figure out what you mean? And what are the rules for that figuring out? Are those rules sort of baked into the language, or are those rules something that you can control either in your code or through the libraries that you're using? So let's do a little comparison of simple if statements. So let's start with Java. In Java, I'm going to create an integer that's equal to 5. And then when I want to do an if statement, I have to compare that integer. I have to use a Boolean. So I have to somehow convert that integer to a Boolean. I'm going to use the not equals operator. So the rules for how I convert that are verbose, right? I can't just figure out that this thing is true or not. That is something I have to explicitly say with my comparison operator, and the rules for how I get things there are built in. They're not something that you can change. There are some operations in the language that let you convert integers to Booleans, and that's pretty much all you can do. You can, collect them together through a hierarchy of methods or whatever, but you still have to write it all out. There's no magic way to get from integer to Boolean. JavaScript, on the other hand, I can just do if x, and JavaScript has this sense of, if that thing is a number and that number is not 0, then I consider that false. And if 0 is false and non-zero is true, and that's good enough. So there's some coercion rules, and exactly what those coercion rules are complicated, so they're pretty magical, and they're built into JavaScript. You can't add new ones. If we flip ahead to Python, it looks about the same as JavaScript, but it actually is calling a method on that object that's dunder non-zero dunder. So if you want to change the behavior of whether an object is true or not, that's totally in your power. You just define a new dunder non-zero dunder method, and you can decide how something will behave in an if statement. So that's how collections do their thing. They just have this non-zero method decide whether, if I've got objects in me, then I'm false. If I don't have objects in me, then I'm false. If I do have objects in me, then I'm true. So it's pretty magical, but it's also pretty custom. You have control over that. All right, let's flip to C++. So I'm going to create a shared pointer, which is C++'s weird sort of garbage collection sort of thing. And then I can do an if on that. And what the compiler is going to do is first find if there's an implicit conversion from the class shared pointer. And that might be defined in the class. It might be put in a random header file, or it might be a template specialization where there's a default one for std shared pointer of anything, but I can create a separate one for std shared pointer of foo that's different from the built-in one. And if it can't do that, then it will use the C-like, is this thing not zero for whatever type it is, and you can chain these things together. So that's a little more magical, I think, but it's certainly very custom. You have total out of control over how that happens. So is this a good idea or a bad idea? And I say it's both. We all like magic when it matches our intuition. We all like verbosity when what we're doing is confusing and the verboseness is helping us through it. We all like built-ins when, why need a library if the language does everything I need? We all like customization when our tools are not enough and we need to add to them in sensible ways. On the flip side, we all hate magic when we have no idea what is going on. We all hate verbosity when it's telling you stuff I already know for the 13th million time, thank you very much. We all hate built-ins when they can't do what we need them to do. And we all hate customization when we're in some twisted, library hell where we can't figure out what anything is or what this object even comes from. So if a programming language is a bunch of knobs, and you get to set those where you want on those magic to verbose and built into custom sliders, what are the knobs that we have to play with? Well, in the programming language, how are we storing data? What comes included in your language? How do you compose bits of data together? How do you convert data? How do you not convert data, which is a fun one, because JavaScript, you have no way to not convert data when you don't want to. It's just going to do it for you. Is there a scope to data? Is there a history to data? That's like the debate of should things be mutable or not? Should everything be mutable? Should some things be mutable? In a programming language, we can also talk about dispatch. So we want to execute other pieces of code. How do you find them? Are there situations where it picks between different pieces of code based on the same piece of syntax? So like in an object-oriented language, when you call a virtual method and it figures out which instance you have and calls the right virtual method, that's it doing some magic for you, right? In a language where you have overloading and you can specify the same name for a function and give it different argument types and then it picks the right one, that's another kind of magic that you can build in. There's also the idea of flow. What order are things done in? How do you control order of operations, short-circuiting, things like that? How many paths are there through your code? So do you just have a straight run-through? Do you have some kind of asynchronous method? Do you have something like an exception that allows you indirect code flow? I know I said I wouldn't talk about standard libraries, but in standard libraries, the questions are, do you have composition control? Can you tinker with the standard library? Can you write code that has the same behavior as the standard library and meshes with the standard library? A good example of, I think, a place where you can't is like in Java, string is magical. It's sort of built into Java and it's sort of built into the standard library, and it lives in this weird place in between. You can't make anything in Java that behaves like string. It has operator overloading, and the rest of Java doesn't. Go figure. So when you are trying to integrate, are the features in string like that, are the features in the language somehow different from the ones that you can create in your libraries? Do the included types have magic that you can't change the behavior of basic types in a way that you can for others? And also the standard library, is the standard library big enough? Does it have all the features you want? Or is it possible to kind of add on in a natural way to the standard library? Or are you very limited? All right, so given that, the decisions you make for where you put all of these knobs really have a lot of complicated interactions. Like virtual dispatch, the idea of I call a method on an object and it picks the right one based on subclass, doesn't make sense if you don't have objects that can have subclasses. They kind of go together. So I can't independently make decisions about how I find functions and how I'm going to store data, because they will mesh together in certain ways. If I want to have a language like Haskell that can do pattern matching based on my data structures, then data structures have to be something that I can pick apart in a uniform way, which you couldn't really do with a Java object. That doesn't make sense of what you're going to have a thing that's all the fields, getters in an object. Like, I don't know. So these features of languages tend to bind different areas of the design space together. And that's the key difference between languages. And we kind of become numb to which parts of our worldview have been entangled together. And we just get used to that, and we get ourselves into a sort of rut where we stop thinking about it. And you might ask the question, okay, is there going to be a language that has no entanglement, that I am free to have complete control, and I can do whatever makes sense in the situation? I'm not encumbered by these decisions. And the answer is yes, I know this language. Have a nice day. I don't really want to program in machine language, but that's the one that gives you the most freedom of what decisions you get to put together. We're here using a programming language because we want to make our lives easier. So we're trying to make trade-offs that make sense. So one of the things about trade-offs is they don't work out for everything. If we're going to make some things easy, then by accident we're going to have to make other things hard. So we want to work under the assumption that the things that we're making easy are the things that we're trying to do a lot of. That's the tool that I want. The one that's going to like take 90% of my work and make it go away. And if the other 10% sucks, then like, the other 10% sucks. So let's do a little more classification based on this scheme and think a little bit about how that's going to work. So for object orientation, what are objects? And no, I'm serious. What are objects? I mean, C++'s idea of an object and JavaScript's idea of an object are almost comically different. Like the fact that they're both objects is there's a dot and then you can put something after that. That's about all they really have in common. So object orientation is about tying together data storage plus dispatch. I have this data and I want you to call this function on it all the time. Those two things are now inseparable in some way. That's really the core of object orientation. So when you pick a different piece of code to execute when you call a function of some kind, we call that polymorphic dispatch. You're choosing something different. There's a whole bunch of other kinds of polymorphic dispatch. So in object-oriented language, the thing that you are calling the method on, the receiver in object-oriented, really, really geeky talk, is the thing over which the polymorphism happens. That's the only thing that we get to decide which is the method we're going to use, is what is this parameter when you're calling the method. So let's do a little fun Java example. I have a class A that has a method called int foo that returns 3. I have a class B that extends A that also has a method int foo that returns 4. I create a new B and stuff it into A, and then I call foo on that object, and I get 4. Right? Everyone good with that? Seems sensible enough? Okay, so I'm going to write this C++ version of that. And it returns 3. Anyone want to guess why? Anyone want to tear their hair out and cry a little? Anyone think I'm wrong? Wants to pull out their C++ compiler and test it? So the reason is C++, in Java, when you create a new method with exactly the same signature as a previous method, it overrides it. In C++, that doesn't happen. You have to explicitly say that a method is overridable. And if not, it creates a whole other method that exists inside your new subclass. And then the C++ compiler looks at the type of the receiver, which in this case is A, and that's how it figures out which method to call. So it's going to call this method because this thing is an A. If you wanted the Java behavior, you had to stick the word virtual here, which means that when you create a subclass of this, you can change, you are overriding that method. You are not creating a new method. So that is definitely magical. I don't know if that's good magic or bad magic. It's definitely confusing magic. Let's do another weird one where object dispatch is a little confusing. So in Java, let's say I create an interface A with a method foo that returns an integer, and an interface B that also has a method foo that returns a long. And then I want to create a class X that implements those two interfaces. What return type can foo have? Anyone? Like that, but the opposite. Neither. There is no, you cannot write a class that will implement both of these interfaces. It's simply impossible. Because if you implement whatever return type you have, at least one of the interfaces will be angry with you and will not compile. So C# solves this problem. When you override methods, you get to specify what interface a method came from. So you can have two implementations with identical parameters and different return types, and that's not a problem. And it uses this heavily for the generic versus non-generic versions of certain interfaces. And it's confusing because all the generic ones inherit the non-generic one with all the same parameters, so you have to implement two methods. No, it figures it out whether the receiver is of type A or type B in the reference that you have to that instance of the object. And then if you call it on X, you are simply not allowed to call foo on something which is of type X because X does not have a foo method. Only A or B have foo methods, so you have to cast X to A and then call foo on it. It's fun, right? There are ways of getting around that where you can make one of them unqualified and then X will have that one. Yeah, I know, right? It's a good time. So this is actually more verbose than the Java way. It's less magic. You are explicitly saying, I am implementing this method from an interface. It's not just something that is kind of magicked out of the syntax of the language. So more verbose doesn't necessarily mean simpler. It just means it's more explicit what's going on, even if it's confusing. Because it's more custom in this case. It's both more verbose and more custom, which is potentially more confusing than more built-in. It's a meme thing. But the rules for how all this works is kind of built in, right? You don't have any control over what's going to happen. That's baked into the language. Okay, let's have another fun time. Let's say I create a class A, and it has a method foo that takes an A, and I have a class B that extends A, and it takes, there's a method foo that takes a B, and it returns a different number. So B is now going to have two methods, one that's int foo A and one that's int foo B. So if I create a new B and I call foo on it with a new B, we expect that to return 2 because the receiver is a B and the parameter is a b, so it's going to pick this method. If I create a method if I create a new b and stuff it into a variable called a, or a variable of type a, and then I call the method foo on it with a new b, it's actually going to call this method because it doesn't know that this method exists. And the rules of, this could be Java or C#, is that the receiver, that's the thing beside the dot, is what determines which method to call. And this thing only can determine the method to call at compile time. It can't make any difference at runtime. So if it can't figure it out at compile time, it can't do it right. If you want to have the parameters matter at runtime, that's something called multiple dispatch. C# has a weird, quirky way to kind of do this, but it's not straightforward. And at runtime, that means you potentially have a hard time figuring out which is the best match. At compile time, you can just fail loudly and be like, it's ambiguous, fix it. But at runtime, it's you wrote the code that compiled, you expected it to run. And the rules for how to figure out which method to call are complicated and built into the language. So there's a lot of magic, and if you look, there's a wonderful post by Eric Lippert where he explains exactly how the C# compiler figures out which method to call. And it's like a 20-page algorithm to figure out which method to use. It's not a straightforward thing to do. So these are very complicated built-in rules. And normally you don't get cases like this, so you don't see this kind of thing. But in either case, those rules are part of the C# or Java spec. You don't get any control over them. You could design a language where those rules are definable in some way. You can say, this is the overload I want you to use. That is a system called predicate dispatch. And when you have a lot of functional languages with pattern matching, that's basically a form of predicate dispatch where it's at runtime figuring out which version of that function to use based on some really complicated rules that the rule just gets to say, yeah, I'm the function you should call. I win. And that can happen at runtime. All right, let's do another fun thing and then we'll start putting pieces together. How many exit points does this Java method have? How many people think 0? It never exits. No one's going for that? Okay, 1 exit point. You know this is a trick question, don't you?
I'm gonna say 3.
Okay, that's an exit point, right? That's an exit point, so we're at 2. That can throw an exception. So this... it could also fail to exit. 4. Oh my god, I'm wrong. I'm in shame now. I'm honored. So in C, there's only 1 exit path. You can only return from a function. Java and C++, you can return or you can throw. Python has return, throw, and yield. C# and later versions of JavaScript, you can return, throw, yield, or do the whole async thing, where you eventually come back from the event loop in some complicated way. So the more kinds of flow control you add, the more magic your program gets. But the flow controls are built in. I mean, sometimes you can build really interesting things out of them. Like you can do a lot of evil fun once you have yield in your language. You can definitely make some completely mind-boggling flow to your program. But yield is ultimately kind of limited by the language itself. We can build new classes that take advantage of these pieces of flow control, but we can't really define a whole new kind of flow control. That's something that's baked into our language. So what if we wanted a programming language where we had custom flow control? You could define new flow control in your library. What would that look like? Can you possibly imagine? That's what monads are. They're user-defined flow control. Mind blown, right? So no wonder they're difficult to understand. If you're used to having flow control just be something that's like built into your language, it's a really weird idea to suddenly take flow control and put it into the library. So yeah, monad is basically a declarative way to create custom flow control. And you can create monad-like things in other languages, but they're always kind of like weird and kind of sad. And the reason is, yeah, those languages already have a flow control system in them. Why are you trying to create this flow control system and just kind of like ram it in? It doesn't really do anything. Now you might ask the question, why would anyone want custom flow control? Like transactions. Like, have you ever used Spring's aspect-oriented monster that tries to create custom flow control by rewriting bits of bytecode and injecting a whole bunch of nonsense? Spring! If you just had some kind of transaction-aware monad, then you could have transaction-aware flow control. That would be like the sensible thing to do. Resource management. You know, a lot of languages now have this try with resources with in Python using in C# construct that lets you try to manage resources. You could do that with a monad because it's kind of a flow control operation of when I'm done with this thing, make sure to clean it up. Whereas in Java, you have to stick in this thing, which is, okay, I need to interrupt the flow control that you are already doing to make sure that I clean up your resources. Thank you very much. Which brings us to resource management, which is everyone's least favorite topic. So in C, you get very verbose, very custom flow control resource management, because every resource is a resource for you to manage totally at your complete understanding of every little corner case of how that works and every possible exit point from every function that you've ever written, and that's fun. In older C++, they had this sort of resource management thing that was a little bit more magical than C, called resource acquisition as initialization, which is basically C++ knew how to clean up certain resources if you declared them in exactly the right way. The C++ compiler could generate the code to do the cleanup, and that was kind of nice. In the meantime, Java, C#, and friends, they're like, we're going to manage memory for you, because that's the only resource that matters, right? Right? So they gave you completely magic built-in control of memory. And then everything else, you can see that yourself. There's the try with resources pattern in a lot of those languages, but basically, if it's not memory, then you have to manage it, just like you did in C. Meanwhile, C++ was developing, and they built resource acquisition as initialization plus templates into this super sophisticated and kind of insane resource management system that was also very fragile and would blow up with template errors that no human could possibly understand. But it was a lot more custom, and it was, pretty good. And then the Rust people came along and said, what if we do that, but it doesn't suck? We'll just build that into the language. We'll make it not custom, or make it not as verbose. We'll make it more magic, but you'll still have custom control over how resources are managed. Ta-da, resource management. So a question that I've been thinking about now is, what does custom dispatch look like? Swift, Apple's iOS Objective-C wrapper language, has been taking a step in this direction. They have these extension things where you can basically say, I have this class that someone else made, and I have this interface that someone else made, and this is how you put them together and make this class implement this interface, even though that wasn't something that the original author intended. Yes. You still have to deal with the permission, the visibility that's built in, so you can't access any private variables in your implementation, but at least you can implement a new interface. I gave a talk before on invoke dynamic, and like if you wanted custom dispatch, I'm sure you could invoke dynamic this into some kind of magical unicorn of insanity. If you're looking for a weekend project, go for it. So in pretty much all languages, how you find libraries and how you version libraries is something that's really, really built in. The JavaScript people are like on the cusp of trying to take actual user control of this. I don't know if they'll get there. They might. It might be really bad when they do it, but it's an interesting first attempt. I'm going with that. What does custom inheritance do or look like? Like right now in Java, how you inherit from one object to the next is based on rules built into the language. You can't say, I want a new way to inherit stuff. We kind of, in the way that Java programmers never seem to be satisfied with what Java is and are always trying to make it something else, there is certainly a lot of Hibernate and Spring approaches to, well, if I just rewrite bytecode enough, I can change the way that inheritance works. Which is not a great idea. I previously worked at Google, and they had a crazy internal language that kind of had custom inheritance. I've been working on a derivative, and yeah, you can do custom inheritance. It's really, really weird, but kind of amazing. What does custom scope look like? Once again, the crazy Google language kind of had this, and it was really, really mind-breaking. R actually kind of has this. Because the scope is a runtime scope, you can manipulate how scope works as part of your running program. Most of the times that people do that in R, it is a horrible bug that they have not intended, but it is theoretically possible. What do custom literals look like? So, I mean, in most languages, you can write a string, you can write a number, maybe if you're lucky, you can write a regular expression. C# and C++ have this idea of you can just put in some curly brackets and some stuff, and it will sort of figure out which constructor you meant to call and like let you do that. But there's no way you can create a like totally new piece of syntax in a language. That's not a feature that any language I'm aware of that's in common use has that. But that's totally a thing that you might want control over. Right now, syntax is totally a built-in thing. So if we're going to talk about the differences between all these things, let's talk about the words that we use. Whenever we reduce the magic and go from something that is more magical to something that is more verbose, these two down arrows here are, you know, if it's fairly built in, we talk about usually it's getting clearer, right? It's clearer as to what's going on. Even in the custom world, it's more understandable because you're writing words to tell you what's going on. On the flip side, when we transition from something that is more verbose to something that's more magical, it's cleaner. I'm telling you less irrelevant stuff, or it's easier, right? There's less that you have to specify. It's easier. Similarly, on this custom to built-in kind of axis, whenever you're going from something that is more custom to more built-in, it's control, right? You're getting a simplified kind of approach to it. And the other way, when we go from something that's got a lot of built-in to more custom control, it's expandable, it's extensible. We love those words. This is when we're happy. Then there's the angry version of this diagram. Whenever we go from more magic to more verbose, we're adding boilerplate and redundancy. And whenever we're taking it out, then we're making it dangerous and inscrutable. Whenever we're going from custom to built-in, we're making it more arbitrary and limiting. Whenever we're taking it from built-in to more custom, it's unnecessary and too complicated. So let's look at some of these decisions. Let's argue about Java versus Haskell. So if we talk about flow control, well, I already said that Haskell has these monads, so you have custom flow control, but it's very verbose. You have to specify exactly what the flow control is. Java, built in. You get exceptions, you get sort of normal method flow, and that's it. And how exceptions work is kind of magical. Like, you really don't, where does your exception handler end up? Like, depends on runtime environment, who knows? Inheritance in Java is pretty magical. Like, this thing extends that thing, and suddenly I have a bunch of variables that I didn't know existed. Neat. But all the rules for how those variables, get mashed around is totally built in. Haskell, you want to compose data structures? You compose data structures. Have a nice day. That is totally your job now. The rules for that are pretty built in. There's only so many, you have to create a data structure from existing data structures. There's no, I just want to magically glue these things together. Dispatch in Java is pretty magic. Virtual method dispatch, it just kind of happens. And the rules for it are kind of built into Java. In Haskell, it's very verbose, and that's it. There's no weirder ways to do method dispatch. Data composition, again, Java, because of the way inheritance works, you can do a lot of really weird, complicated data composition, especially once you get into inner classes. You can have a grand old time. In Haskell, nope, you're doing that yourself. But function composition is where this kind of flips. In Java, you want to combine functions, you want to combine methods, yeah, you do that. In Haskell, there's all kinds of weird operators and things to let you smash bits of function together and create whole new functions in ways that may or may not make sense. And Java has a lot of intermediate types that you have to specify as you're writing your program, whereas Haskell's type inference system just kind of, yeah, I can create some kind of weird polymorphic type with 30 substitutions. It's fine, don't worry about it. Just go on about your day. Okay, let's talk Java versus JavaScript. So dispatch in JavaScript is actually more verbose. The class hierarchy doesn't exist in JavaScript, so you have much more control over where a method actually is and where it's going to be called from. Java actually has a more custom type system than JavaScript because you have that class hierarchy. In JavaScript, you get your limited set of internal types, and you have, type of an object is object, not the actual instance of that object, whereas the equivalent type of operation in Java says, oh no, it's the thing you made. JavaScript has some really magic function composition when you get into all the function dot apply bind stuff that never works properly, as you found it on Stack Overflow. Scope in Java is kind of magical because of the way inheritance works, but in JavaScript it's even more magical because it can kind of get things out of certain global state, and there's some local state, and then there's the captured state. Scope is interesting. Okay, so what are we going to do with all this? The more verbose and built-in something is, usually the easier it is to learn. It's usually an easier transition. Things are often tied together. So although we might make one dimension simpler, it's bound to something else that's going to get more complicated. So there's always a trade-off. So Go tries to be the ultimate in verbose and built-in. It's very easy for everyone to learn, but you don't really get a lot of abstraction, and you don't get a lot of the magic that's saving you coding in the long run, which is why every Go program looks like, look, I get to re-implement a hash map for the type that I made. And I don't know about you, but I'm looking for abstraction. I want stuff to be easy, and I'm willing to pay some, okay, sometimes it's going to be confusing cost to get there. And part of the problem is that learning pieces is hard. So I said this before, you can write monads in Java. Java now has an optional monad. Yay! They're kind of weird. It doesn't really fit with the rest of the architecture of Java because Java already provides a bunch of things to do what those monads are doing. So, I've seen these tutorials of here's monads for Java programmers, and they give you a bunch of Java code, and it's like, no sane person would write Java like this. This is absurd. Why would you do this? So when you have so many complicated interlinked decisions, it's hard to move and to learn things in little pieces. You kind of have to jump into a whole new world. And importantly, the different pieces really connect. So yeah, why would you want an optional monad when you have null? and exceptions. Like, it doesn't make sense. Similarly, adding null to Haskell is like a stupid idea because everything is monads. Why wouldn't you just use an optional monad? So good tools have decisions that are complementary, where the decision you make in one part meshes nicely with the decisions you've made in another part, and they support each other. The crappy parts of languages are where your two decisions fight each other. So like Java's arrays and primitives are like weird built-in little magic type entities in an otherwise custom and verbose and custom type system. Like, why? Why would you have these things? They don't fit. With, try, and using constructs are trying to put a very weird kind of resource management into a system that was built to not have to do resource management. That's why they're always awkward. I think programmers also grow with their tools. We see a crate of new programming languages that are simple at roughly constant rate over time. And like Java was simple in Java 1.0. Java 10 is not simple anymore. And the thing is, a whole generation of programmers grew up with Java getting complicated. And then Ruby was simple, and now it isn't. And a whole generation of programmers, they're almost reaching their maturity point of we have created the crop of Ruby programmers, and that's kind of that life cycle. We can move to a new generation. And the Go people are doing this now, and they're having this like, maybe we should add generics. It's like, yep, yeah, you'll get there. I would also say scope matters a lot. So if any of you use the tool JQ, is a little programming language that lets you slice and dice JSON files. It's really magical, but it's not too bad to learn because there isn't a lot of it. The more general purpose your language is, the harder it is to get a hold of just because there's so much stuff. Whereas XPath, CSS selectors, SQL, they're all languages, but they're generally so constrained. And I mean, CSS selectors are now Turing complete, but I hope to God no one would use them that way. And I don't think the authors intended for anyone to use them that way. One of the other things that I would say as a general feeling is that built-in things tend to be less consistent over time. They're arbitrary and they're baked in. And so because they can't be modified, people sort of can't rail against them in a meaningful way, and they can't be changed without breaking all the programs that exist. So like JavaScript's casting we're stuck with it forever. There really is no way out of JavaScript's casting without developing a whole new language that happens to look like JavaScript. Libraries are a lot easier to change. So bad parts of libraries just get deprecated and go off and either become disused or actually die and get removed. But bad parts of languages are a lot harder to kill. And I think there's no perfect language. It's impossible to create a tool that is going to make everyone happy. Magic, adding it will always improve productivity at the expense of comprehensibility, and customization will also improve productivity at the expense of future compatibility. And there can't be a perfect balance. I think because each of us is different. We've each had a little life history of what code bases we've dealt with, what languages we've learned, and we've been exposed to different magic. And once you've been exposed to that magic long enough, you just sort of, it blends into the background. It becomes a thing that's just normal. Of course, that's the behavior that I expect. And each problem that we want to solve has a different hard part. And so we need different languages that do the hard parts differently because of the nature of the domain space of the problem. So where do you go from here? So much of languages are aesthetics. So the ones that get popular are generally going to tend to be more verbose and more built in and use kinds of magic that are popular in other languages because people will be able to switch to that language if it is familiar in certain ways. So here's the sad version of my conclusion slide. You're a collection of your past experiences. No tool will ever make you completely happy. No tool will ever work for everybody. Learning a new tool either requires picking tools that are so similar to your existing ones that there's not a lot of mental adjustment, and that means you're going to get more or less the same features and deficiencies as the tool you already know, and so the incremental benefit of learning them is small. Learning a completely different language will be completely different ways of thinking, which is going to be a lot of work. You get to go back to your like noob days with this programming language of trying to figure out basic stuff like how do I deal with a file, and then once you finally get to the point of I love this thing, then convincing all of your friends to come along will be hard because they have to go through the same emotional journey that you went through. And even if you go there and learn a bunch of things and then want to go back to your previous tool and apply them, they won't work so well. Okay, let's do the happy conclusion. You're a collection of your past experiences, and you need to convey why the tools that you like have value to you. When picking tools, you need to understand why their features are matching the needs of the problem, and you need to convey that this bit of magic is a useful bit of magic and worth the burden that comes with both learning it and the other deficiencies of this tool. And being upfront about those deficiencies, helps people. If you sell something as this is going to be great, then when it's not, everyone is let down. Set expectations reasonably. Like, this is going to be really good for transaction and suck when it comes to data composition. Sorry, but trust me, since we do nothing but transactions, it'll still be worthwhile. And to teach patterns of thinking is useful, and that is different from teaching patterns of doing. This is kind of why I hate the design pattern book. I hate design patterns, but they're all about ways of doing things rather than ways about thinking about problems. One of the things I would say is there's this iterator versus enumerator problem, or a numerator pattern. And I can create a class and call it iterator, and that doesn't help me. The iterator and the enumerator pattern differ in who has flow control. The thing consuming or the thing producing? That's a much better way of thinking about that category of problem. And you can do that if you try to understand the experiences of the people you're trying to convince. And when you do that, don't show them the easy parts. Don't show them like, look, we have arithmetic and it's the same. Show them the hard part, the thing that this tool is actually good at and the different assumptions that you need and how those different assumptions get stuff done. So I had a coworker who played a lot of board games, and by a lot of board games, his one-bedroom apartment had 9 bookshelves full of board games. Whenever he explained a new game, he would describe it with, the purpose of the game is to win, not lose, or make someone else lose. That was his setup, and it was a really good setup. It got you thinking in the right pattern about how you were going to play this game. And I wish we had the same kind of approach for languages. So the purpose of this language is to be efficient by, not put energy into, or make libraries do the work of. Those would be my candidates for how to start off describing your tools. And that's all I got.